see you again. So we're going to talk about lecture 20. That's a derivation for the ideal long-channel MOSFET drive current equations. So basically, just a brief review of the qualitative understanding of the MOSFET drive current. Okay. So basically, as illustrated here, MOSFETs are like three or actually more, four terminal devices. Based on our qualitative understanding of the current conduction in the MOSFET, so once we apply, a high enough gate bias, let's say, when the gate bias is over the threshold voltage, we're going to generate inversion charge in the channel. Okay, because in that case, the depletion charge concentration in the channel will be fixed, right? So basically, the added gate voltage will try to boost inversion charge in the channel, so that the gate can modulate the resistance of the MOSFET, okay, transistors, okay. And also for the three-terminal device applications, we may also apply a drain bias, which is higher than the source bias, so that we can keep inject electrons from the source to the channel, and also we're going to flow a current from the drain to the source, right? From the high potential terminal to a low potential terminal, okay. So this lecture we'll do some quantitative derivations for the drive current, under those some bias conditions, okay. So as we know, the current mechanisms, across the MOSFET channel, on-site when the gate voltage is over threshold, there will be the drift current, okay, by the electrons, okay. And also, the most important parameter, for us to figure out the drift current is actually the threshold voltage, right? Right. So basically, only above, like only the gate voltage is above threshold voltage, then we are able to, drift electrons to form current, okay. And also, before we derive the threshold voltage for the three-terminal MOSFET transistors, I'd like to, review the threshold voltage expression for the two-terminal MOS capacitors, okay? So that would be flat band voltage plus twice the buck potential, right? That's the surface potential of the silicon. And also that would be the potential drop at the silicon channel. And plus, the last term would be depletion charge over aerial oxide capacitance, right? So basically, that's a two-terminal threshold voltage for the MOS structure. And two-terminal means you're only able to generate the 1D, one-dimensional, potential profiles vertically across this structure. Basically, that's along the x direction, right? That's how basically they're going to modulate, the electrostatics of the device in the two-terminal MOS capacitor, okay? But things are going to be, a little bit difficult here. So right now, if we have another two terminals, which are actually source and drain, and we keep applying another voltage laterally across the MOSFET channel. And actually, due to a very simple superposition rule of the potential profiles, actually right now we are dealing with a 2D potential problem, right? So if you compare the threshold voltage expressions, as listed here, so instead of the original threshold voltage terms we derive from the MOS capacitor structure, well, actually you're going to find extra terms. The first is V sub CB, denoting the voltage or potential drop, from the basically along the channel, and actually that's a function of Y, right? So basically Y is your current flow, the lateral direction. So right now, if I apply usually, is higher potential, higher bias in the drain side, basically higher bias in the source side, then basically you should expect a voltage drop, laterally from the drain to the source, okay? So if you still look into the source end, so basically the channel region, but very close to the source terminal, then basically the potential here, the VCB is going to be still zero, right? Because once you ground the source, and actually you only generate a voltage difference from the drain to the source. But very close to your ground terminal, they're going to be zero. But if you look into the drain end, basically the region we call for the silicon channel, but close to the drain side, that's going to be your drain bias, VD, right? So basically you are expecting somehow voltage drop from VD to ground along the channel direction. And basically that's why we call the VCB the function of Y, okay? And we're going to see the impact of that term, affecting the overall MOSFET threshold voltage. So basically, in this picture, the threshold voltage of a MOSFET is no longer uniform, right? Because you have extra components from the lateral direction, and actually that terms contribute to the overall channel potential of the MOSFET. This is one of the reasons why it's not uniform. The second reason is that if you look into the depletion charge, we developed previously, there won't be that VCB term, right? There'll only be the twice of the phi f, right? And actually that term is actually the total voltage drop across your gate outside, right? There's some charge, you always generate some charge to balance the depletion charge as well as the inversion charge in the semiconductor region. So basically that denotes the voltage drop across the gate stack, okay? And once you have non-uniform depletion charge distributions, right? You have different depletion regions as well as depletion charge along the lateral direction. So basically, if you really look into the voltage drop across the outside, because you always have the charge you generate along the basically from the gate, well, that's always uniform, right? Because the gate is kind of like conductor. But since you need to use the charge on the gate to balance with the charge in the second region, and that's actually some term non-uniform, right? So basically, you need to take that into account of the lateral voltage drop or the potential difference. So somehow you're expecting the voltage drop across the outside will also depend the distance you look into, right? Will be also a function of y, okay? Will be also vary versus the distance, right? Okay. So in that case, if we still basically want to turn on the channel, still want to enhance the potential here to reach a threshold, then basically the two non-uniform components, two non-uniform terms we take into account. The first is a contribution from the lateral biasing, right? The lateral potential difference. Then the second term would be the impact of non-uniform depletion charge along the channel. Okay. So in that case, the threshold voltage of the MOSFET will be quite different, along the channel direction. If you still look into the region around the source end, there's a region near the source terminal, basically VCB, the two VCBs will be 0, right? So in that case, somehow you have like a smaller threshold voltage values, right? But well, that's corresponding to you have basically the minimum depletion charge as well as minimum depletion region width. But somehow, if you shift your attention around here in that region, and where you have a maximum VCB value, so in that case, you're going to have larger actually voltage or potential actually contribution from the drain terminal, which you're actually going to reach maximum depletion width as well as depletion charge concentration here. Okay, so basically you're going to know that basically the message here is like threshold voltage as well as depletion charge will be uniform along this direction. And around the source direction, both the two parameters like threshold depletion charge will reach their minimum value. And if you move to the drain side, both of the two are going to reach their maximum value. Okay, and so what's the consequence on the inversion charge? Because we know that based on the expression, the inversion charge is equal to aerial capacitance from the gate outside times the gate overdrive voltage, right? So basically, there's a gate bias subtract all the terms appearing in the threshold voltage expression. So basically, once you have non-uniform threshold voltage appearing here, and of course, the induced inversion charge along the channel will also be quite non-uniform. Okay, and also due to the fact that once we induce some charge on the gate to balance the inversion charge as well as depletion charge, then basically the concentration of the two, inversion charge and depletion charge, they tend to trade off, right? But once you increase the depletion charge for the fixed gate bias, once you increase the depletion charge here, for example, closer to the drain side, basically simultaneously at a fixed gate bias, you reduce the inversion charge concentration. Okay, and well, for the source side, because you have the least depletion charge here, so basically at a certain fixed gate bias, you're expecting to see the maximum concentration of inversion charge. Okay, so basically, for the inversion charge, is actually, which is just gate capacitance times gate bias subtract Vt is a function of distance here along the y direction. So somehow we're expecting to see quite non-uniform, right? distribution of inversion charge, which have to be balanced, with depletion charge. Okay, so all the facts tells us, we need to rederive for the threshold voltage expression for the MOSFET once we take into account, actual potential contribution from the lateral direction, right? Once we deal with those 2D, two-dimensional potential profiles problems. Okay, so if we go back to see the threshold, the re-expressed threshold voltage expression here. Okay, so basically all the other terms look straightforward. Okay, basically just from the difference of the terminal voltages, right? But the only thing we need to deal with here is like recalculate the depletion charge. Okay, and which we also need to take into account, basically the variance versus the channel length versus the channel length distance versus the distance along the channel length direction, right? So previously we know that depletion charge is proportional to the square root of the semiconductor potential, right? So for the 2D, two-terminal MOS capacitors, right? So basically the semiconductor potential is just twice of the phi f. But right now, if we take into account the contribution from the drain terminal, okay, so basically that's what you see. We need to basically we need to pass the potential drop laterally. And basically for simplicity here, we just want to simplify our derivation. Basically we assume that's actually our first order approximation. We just think about the potential is equal to VSB. Stands for the voltage difference closer to the source side, in the source end. That actually would be, a maximum number of inversion charge corresponding to the least number of depletion charge here, right? Because VCB will increase as the distance y, increases, right? If you move to the closer to the drain side, basically the contribution from the drain will be larger. But somehow we just take the approximation here. We just use a minimum potential, which is VSB, the potential difference from the source to the substrate, okay, to derive the depletion charge expression here, okay. So in that case, we may rewrite the threshold voltage, okay, by playing some tricks here, okay. We just, add those, we just get, the VSB dependence involved, okay. So in that case, somehow we can simplify this expression of the threshold voltage, which is still, like distance dependent, right? Depending on which position you look into in the channel. As a function of redefined VT, we substitute here, subtract, the difference between the source and the body, and plus the lateral, continuous potential contribution from the drain. Okay, so but the reason I mentioned that's a redefinition of VT here. is like if you try to, go back to the previous expression and you want to expand the VT terms, actually what you can find here is VT is actually consists of the potential difference, include the potential difference, between source and body, okay, as well as here, okay, which is quite different compared with, what we define from the two-terminal MOS capacitor, right, in which this term will just disappear, right? This term will be 0, okay, because right now we shift somehow our attention from the substrate to the source, and we're going to take the source as a potential reference. So basically, that's somehow we redefine everything according to the source potential. So basically, since it's not necessary for us to take into account the voltage difference between the source and the substrate. Okay, so right now that's our redefined VT, and since along the channel direction, VT is a function of basically at which distance, at which position you look into, right? And also the same thing I like to re-emphasize here is also like closer to the source side, you're going to have the minimum potential here, minimum VT values. But at the drain terminal, you're going to have VT, reaches the maximum value, right? Due to the large contribution from the drain bias. Okay, so right now, if we want to re-express the inversion charge concentration So basically, we just plug in, this term, okay? Basically, we just made the inversion charge concentration as a function of y, okay? Depending on which distance you look into, at which position you look into, okay? So basically, Q inversion right now is equal to aerial gate capacitance times gate bias subtracted by threshold voltage, basically redefined value according to the source potential, plus the difference between source and body potential, and and minus basically contribution from those drain terminal, right? So also, if we re-express those, we're just going to map those values to the terminal voltages. So basically, this is like the source bias, right? And also, this is going to be the channel potential as a function of distance. Okay, so before we get to derivation of the drive current, okay, let's try to analyze a problem of looking into the MOSFET device, okay, with the source drain. Okay, once we're going to form some channel. So basically, in that case, the MOSFET itself just looks like a semiconductor bar, right? Once we apply some voltage across it, we are expecting some drift current through, right? But what I like to do the thing here is once somehow I increase the length of the semiconductor bar by dy, okay, with the DC current flow through as IDS. That's a current from from the drain to the source, okay? And what I like to see is the voltage difference, induced by the increment of dy, okay? So let's say I just keep the drive current as IDS. Somehow, I just put an increment to the length of my channel as dy. Then basically occurs, there's actual voltage drop across it, okay? But so basically the D we see, there's the increment of the channel voltage drop is equal to the DC drive current IDS times the equivalent resistance of that increment of the semiconductor region, right, of the channel region, okay? And also, according to the definition of the drift, resistance, or just a resistance of a semiconductor bar, which dr is equal to resistivity rho times the length of that semiconductor bar, that small portion, right, is dy over the cross-section area of that channel. That's basically, for the MOSFET device, that's equal to, so think about how going to flow the current in the MOSFET literally, right? The cross-section would be the channel width times inversion thickness, right? We assume, although we know that inversion layer would be very thin compared with depletion width in the MOSFET, but we're still going to assume some finite value here, okay, for the total thickness of your MOSFET conducting channel, okay. So basically, if we just rearrange the terms, if we just combine the two relationships, we're going to get the voltage difference due to the increment of the MOSFET channel is equal to IDS times dr here, which is equal to IDS times resistivity rho times the increment, the length is dy, divided by the cross-section of the MOSFET drive current. It's W times the inversion, okay? And also, according to the definition of drift resistivity, rho is actually 1 over charge Q times the inversion charge concentration. That's the volume concentration of inversion charge times carrier velocity, carrier mobility, effective mobilities, right? Pay attention here is like the quantity N here has a units of per number per volume, right, per cubic centimeter, okay? And also, so basically that's what we get, okay? That's equal to proportional to ID times dy divided by the long expression. And also here, we would like to rearrange the terms. Actually, somehow, we can actually combine those three terms, those three quantities, the Q, N, and W here, Q, N, and T inversion here, by redefining a quantity called the aerial inversion charge concentration, which is equal to Q times N times T inversion, okay? with the units of Coulomb per area, right, per centimeter square. That actually talks about, okay, so what's the areal inversion charge concentration, right, per area you're going to have in the MOSFET channel at a given, gate bias, as well as some other conditions, Okay, so in that case, somehow we got this relationship here. And we may also shift, the denominator here to the left and perform the integration on both sides, okay? We're going to do the integration starting from the source side of the channel, source of the channel to the drain, to the drain side of the channel, okay? So basically, for the integration of those increment, we need to do that from 0. 0 we call as starting point of the channel, that's the source side, to the basically the region closer to the drain terminal, that's basically the channel length, right, at the distance of L channel length, okay? Regarding the right-hand side, if we want to do the integration over the channel, so basically we just do the integration of the bias starting from source voltage to the drain voltage here, okay? So as I can see, since the drive current IDS, okay, that's a constant versus distance, right, due to the current continuity law, basically the integration of the left-hand side just becomes IDS times L. And then you may also shift the L to the right, so basically it becomes the denominator of that term, right? It's like W over L here. Or the same thing like you can do for the right-hand side, okay? Eventually, you see only the bias-dependent term will be basically, that, the expression is going to basically get, try to calculate the areal inversion charge, right? Which is equal to areal capacitance, gate capacitance times the gate overdrive voltage, which is also, position dependent, okay? So turns out that if we just do the integral versus VC, that's the channel potential. Sorry, that's that's actually the contribution from the drain terminal, right? So basically, that's a contribution of the lateral voltage drop, okay? And if you just do the integral of that, it turns out that basically there's a linear function. If you do the integration, you get like somehow a quadratic dependence here, right? Okay. So also, it turns out that eventually, if you look into the final expression of the drive current, somehow you're going to find that it's proportional to W over L. So basically, that's interesting thing to note. Compare with some previously learned semiconductor device. Instead of the absolute, this is the absolute drive current value, right? This is the absolute current value. Instead of depending on the cross section of semiconductor device, it's only a function of aspect ratio of the channel. Okay, so basically, it only tells you that it only depends on the ratio of channel width versus gate length, right? So basically, this actually itself, proves that MOSFET itself, is basically is a surface device, right? It's quite different compared with the previous, the device you learned, like Schottky diode as well as PN diode. In which once you calculate the absolute current, you should use the current density times the cross-sectional area. But for the MOSFET itself, it actually seems only proportional to that ratio. Okay, and also pay attention to here is like once you use the capacitance value to calculate the current through a MOSFET, you should use the areal capacitance, right? That's like farad per centimeter square, right? Once you also use, I guess, the same quantity to calculate, inversion charge concentration. The same thing here, okay? And also, all the derivations based on, we assume we operate the MOSFET in a linear region, okay? In which if we keep applying the drain bias, we're expecting to see, basically the continuous current enhancement, right? So basically, we're just enhancing the lateral field so that, we're going to have larger and larger drive current, okay? So basically, there's a linear region where, VDS is actually smaller than VG minus VT. Okay, turns out that, pay attention here, the newly defined VT should be with a potential reference at the source terminal rather than with a substrate. Okay. And also you can imagine about the current drive current expression for the MOSFET in the saturation region, right? Once you apply a higher enough drain bias, you have some pinch-off region in the channel. So basically, the current is just going to saturate at a certain value. If you just keep applying bias beyond this point, so basically all the voltage will be dropped in the depletion region, right, in the pinch-off region. Okay, so basically, but if you look into the whole range, the current versus voltage characteristics should be continuous, right? So basically, you just, once you see the region of the saturation, basically you just pick up the voltage here at those saturation edge, right, which is basically at a VD of Vg minus Vt, and you just replug in the linear drain current equation. You can get the expression for the saturation region drive current. Okay. So also turns out that it seems like the drive current is also proportional to the aspect ratio of your channel width versus your channel length. Okay, but as in a dependence versus basically the gate overdrive or gate voltage, instead of you see a linear dependence at a lower VDS bias, right? As you see linear dependence here. Oh, sorry, yeah. So roughly, this expression gives you linear dependence because usually when VDS is small, okay, you can just ignore this term, okay? This term can be ignored when VDS is small. So somehow you see IDS is a linear function of gate bias, okay? But if you compare to the saturation region current, as you can see, basically the drain current shows a quadratic dependence versus the gate bias, right? This ID set is proportional to Vg minus Vt squared, okay? And also basically just pay attention to the definition of Vt here, okay? So basically we just have we just take the reference of the source. So basically you need to consider about the difference of the source bias compared with substrate bias. Okay. And also I'd like to mention that for our first order approximation, basically we ignore the spatial variance of those diffusion charge. Basically, as you can see, which is proportional to the square root of the channel potential at a certain point, at a certain location. But which is also supposed to be VCB as a function of y, right? As a function of the distance, because you're going to have a non-uniform distribution of those from the potential contribution from the drain side. But just for simplicity here, although we do take into account the contribution from the drain bias, okay, by writing the VCB as a function of y terms here, and that's what which we're going to use to calculate the inversion charge at a certain distance. But just for the channel depletion charge, we will assume it's a constant, and it's equal to the depletion charge at the source side, at the source end. Okay, so basically that's our approximation, and also under which that's what we get for the current expression in the two regions. Okay. Are there any questions so far? Okay. Okay. So right now, I'd like to examine, basically examine what are the deficiencies of those assumption, because basically somehow we just think the depletion charge is uniform along the channel. So basically, as we can see here, this our expression, once we assume the depletion charge is uniform, and because the gate charge, the charge induced on the gate also have to be uniform, right? So basically, as a consequence, under this model, under this assumption, the derived inversion charge concentration also have to be uniform, right? Also is uniform along the channel, which is only a function of, basically is a function of Vt, because Vt is uniform, and well, the inversion charge is not uniform, but the thing here is like the Vt is uniform. And non-uniformity will only be reflected by the term of minus Vc, right? That tells you about a different position have different, channel voltage, channel potential drop. Okay. Okay. But think about in reality, once you have a MOSFET channel like that, and once the gate voltage is above the threshold voltage, you're going to have a non-uniform depletion charge distribution, right? Like illustrated here. Well, the region, if you have the region closer to the drain terminal, so basically, the drains basically you have very high terminal, is likely, reverse bias the p-type substrate, right? So basically, enlarge the depletion region. So basically, around this region, you have larger depletion charge. But in the source terminal, you're gonna use that as a ground, and also you have less depletion charge here. Okay. So basically, that talks about in reality, once you have those uniform, non-uniform depletion charge distribution, let's say depletion charge increases with y. Y is your channel direction, which causing the threshold voltage also increases with y, right, with the distance along the channel. Okay, so basically, as a consequence, if you like to evaluate the real inversion charge concentration, Q inversion here, because this term keeps increasing, right, as you move, as you increase the distance here, as you're moving from the source to the drain terminal. So basically, Q inversion will actually decreases more actually with increasing y, right? So basically, even under our first order assumption, we know that inversion charge is going to keep decreasing here, right? Because you have higher potential here. Actually, you have end up with larger depletion width. But the things like because you have larger contribution, water drop from the drain, which is biased at a high voltage. But in reality, Q inversion will actually decrease more because you have non-uniform depletion charge distribution, right? So in our first order approximation, as you can see, as long as we think Vt is not a function of the distance, then basically Q inversion only depends on the channel potential here, right, which contributed from the drain. But once you think even Vt will change versus the distance, and actually Vt will increase as we move to the drain side, then basically if you re-evaluate the Q inversion, you'll find actually the Q inversion will decrease more, right, compared with what we assume in the first order approximation, okay? Okay, so basically in that case, once, if we go back to revisit the current expressions we derive from MOSFET, somehow we're going to feel that, we somehow overestimate the inversion charge concentration, right? Just because, we didn't take into account the spatial change of Q depletion here. But somehow, and Q depletion have to be balanced with Q inversion, okay? Actually, the two concentrations are going to trade off each other. So somehow, once we overestimate Q depletion, so somehow it's like, somehow we just once we underestimate the Q depletion, basically the same thing like, we overestimate the Q inversion here. So basically, the consequence would be Q inversion is overestimated. Well, the same thing, for IDS, right? IDS is also overestimated. Okay? Because once you have less inversion charge, in reality, of course, you should expect less drive current, right, from the MOSFET in reality. Okay? So also, that tells about something about, regarding once, the mechanisms, the MOSFET saturate at a pinch-off state, okay? So basically, let's talk about once you apply a high enough drain bias, you keep, generate a large, let's say, large enough depletion area or high enough depletion charge, okay? So basically, you won't have, any inversion charge form at the surface of the MOSFET, right? So basically, that point is actually we call the saturation edge, right? Your channel starts to pinch off, okay? But in our first order approximation, as we described previously, somehow, if we underestimate, depletion charge, that actually tells about, basically basically with the underestimation of the depletion charge, we get the saturation voltage is equal to Vg minus Vt, okay? But so in reality, if you make the corrections about depletion charge, so because this is underestimated, right? So basically, in reality, you're going to have actually more depletion charge, okay? The consequence of that is, if you look into, the position, the pinch-off point, you derive for the approximated ways, but in reality, around that position, around that location, you're going to have over-depleted, right? You're going to have more depletion charge. So basically, in other words, this actually, in reality, the saturation voltage could be even smaller than this value, right? Because you underestimate depletion charge. But if you just take into account Dawes effect, so basically, you're going to have the pinch-off region appears earlier in the channel, right? Than your approximated, models, right? So basically, the consequence would be, in reality, the saturation voltage would be lower than that value. Okay, your MOSFET going to saturate earlier. Okay, so also, basically the easier way, so to take into account of the distance dependent depletion charge is actually by basically remodeling of the remodeling of the saturation voltage. Basically instead of just using Vg minus Vt, so somehow we just introduce a coefficient here. So basically, right now the new saturation voltage, since it's lower, right? We just overestimate that. So basically the real saturation voltage should be the original value, Vg minus Vt, divided by some coefficient M here. Okay. So in that case, we're going to use that, to rectify, to crack the MOSFET drive current equations. Okay. So if you replug in those new relationships, just by replacing the previous Vg minus Vt by Vg minus Vt divided by M, okay? And if you want to rederive for the equations, so basically, as you can see, for a linear region, instead of previously, there's a minus 1/2 of the VDS, but right now what you get is like minus, M over 2 times VDS. The same thing for the saturation current is actually previously the term, appears in the denominator is only 1, right? It's only W over 2L, but right now it becomes W over 2L and also divided by further by M. That's actually going to talk about after these corrections, the drive current from the two regions of both the two regions of the MOSFET will get reduced, right? Because previously, you overestimate the inversion charge, okay, by ignoring the depletion charge dependence, spatial variance. But right now, after this correction, somehow after cracked, the VT distribution, VT dependence, or distribution in the channel, somehow it just get reduced drive current, okay? And also, if you want to, say get values, get expressions of that coefficient, somehow you can prove that, that M is equal to, that coefficient is equal to 1 plus depletion capacitance at the maximum, depletion width, that's actually C depletion mean, right? The minimum value of the depletion capacitance over the gate outside capacitance. Actually, that actually talks about something about, this effect actually talks about something, like charge dividing, or voltage divider is like between your gate outside capacitance versus depletion charge capacitance, okay? The larger depletion capacitance you have, so basically the stronger this effect is going to be, right? So basically you can have more, you expect to see more degradation due to those corrections, right? In reality, you're going to see less current, MOSFET drive current. And also, but thing also talks about, well, the smaller, depletion capacitance you have, then basically you're expecting to see, the less current degradation you're going to suffer from this correction, right? And you're going to have actually larger MOSFET drive current in reality. Okay. Normally, the value of M drops within the range of 1.1 to 1.4. Okay. So basically after that, right? So basically after this correction, the relative error compared with the models we derive under the first order assumption, we will just give you somehow the error range within that. Okay. Okay. So far, we keep introducing the basically the quantities called, variables called threshold voltage. So basically, I made this slide just try to avoid the confusion between the different definitions of threshold voltage here. So in a two-terminal device, like most capacitor structures, okay, because we just take the voltage potential reference as a substrate, as a body, right? So basically, that's how we define every threshold, every voltage is from. I mean, based on, right? So basically, the threshold voltage is expressed as it's only the flat band voltage plus basically the surface semiconductor surface potential and plus twice of those potentials here, surface potential, which is actually potential in silicon, and plus basically that's a depletion charge contribution. That's the voltage drop across the gate outside. So basically, that's based on we look into the voltage difference between the gate and the substrate, right? Okay, we just take the substrate. Basically, we just take the substrate as a potential reference. Okay, but right now, usually for the common definitions of the MOSFET, three-terminal device, somehow we just take the source voltage, the source terminal as a potential reference. So basically, in that case, the redefined VT would be the difference between at a threshold would be the difference between gate bias, with the source bias. Okay, both of them two will be at threshold. Threshold condition. Okay. So just pay attention here. Okay, and also the derived equations for the drain current at different regions. Basically we can re-express basically using as a function of the gate bias, the redefined threshold voltage using this way, as well as the drain bias. Okay, and the further corrections will be made at a dependence of the drain bias is actually which results from the spatial dependence of the depletion charge, right? Actually, we'll find that in reality, basically the corresponding drain current will be lower, right? Will be lower than what we approximate at the beginning, right? So basically, that's why you need to take into account, the impact of those basically body bias, right? Or like the impact of the depletion charge. So basically, that's why you get the drive current always reduced compared with the very simple model. Okay. Okay, so since right now, we have more terminals, then basically we have more impact from the different, from the bias from the different terminals. Okay, so I think it's worthwhile to look into overall the body effect on affecting the MOSFET drive current. Okay, based on the threshold voltage defined here, as we define from the source, right? Okay, so right now, as you can see, the threshold voltage is really a function of basically the substrate bias you apply, right? If you in most of the most of cases of the MOSFET operation, people just ground the source of the MOSFET. But so basically the threshold voltage right now can be modulated by the substrate bias you apply. Okay, so if you draw the MOSFET like this, and say for N-channel MOSFET with a P-type substrate, right? In most of the cases, you just ground the source and apply a higher bias in the drain side. This is your VG, okay? This will be your substrate bias, okay? So in most of the cases, you're going to have substrate bias not equal to 0, okay? That's to say the source and the substrate is not grounded together. So you're going to have this condition appears, that's VSB larger than 0, okay? So, well, that means if you look into the PN junction existing between the source, with the substrate, it's actually you're going to reverse bias the PN junction, right? If you look into the PN junction here, okay? So that's in most of the cases. Because once VSB is larger than 0, so basically the potential in the N region, is higher than the potential in the P region, okay? Can anyone tell me why, in most of the cases, we only allow this condition to appear? Can we do sometimes actually VSB is smaller than 0? Can we? Yes. Yeah, that's true. You're right. So basically, in that case, if you do VSB as negative, so somehow we just allow the full bias of the p-n junction, right? We allow a very huge current components to leak from your substrate, to your channel, which cause basically the problem of the MOSFET, right? Because in principle you only want to control MOSFET using the gate terminal, right? But as long as you can have a leakage path to make your MOSFET conductive, in that case, your gate will just, we're just going to lose the controllability over the channel, right? Can never fully turn your channel on and off. Can never fully turn the MOSFET off, right? Okay, so basically that's in most cases. We only allow, the substrate bias condition this way. We don't allow the biasing the substrate this way, okay? And also, in that case, under this condition, okay, if you like to look into the threshold voltage as a function of substrate bias, VSB, okay, turns out that we'd like to also add another term, as you can see, which actually comes from the zero substrate bias, right? The voltage drop across the outside, right? Okay, so basically, then somehow if we rearrange the terms, somehow we get the threshold voltage is equal to VT sub 0, okay? Basically, just a term, okay? Basically, just the threshold voltage, but just with a 0 VSB, right? If you just ground substrate and source, somehow you just get VT0. Basically, that's the summation of the first appeared three terms here, right? And also plus a difference, basically capturing the potential difference of within reverse substrate bias, subtract the zero bias case, okay? So basically, we call this coefficient here, coefficient as gamma here, which is actually, it's just a term in front of the potential difference here, right? So basically, just square root of twice Q times NA times mu silicon over C ox, right? That's just what that coefficient tells you, right? So basically, somehow we're going to model the threshold voltage as a function of substrate bias, okay? From based on some references, based on some reference value of the threshold, right?